Okay, I think we can go ahead and get started. So yeah, my name is Dylan, and I work with High Performance Research Computing. I work at their help desk. If you've been to any of these other primers, you've probably heard my voice before and probably seen my little picture from Zoom. So today we're going to be talking about SLURM job scheduling. SLURM being the, how do I unpause it? SLURM being the job scheduler on the Terra cluster. So also, like the other primers helping me out today, Braden is in the chat, another student worker with HPRC. So if you have questions, feel free to drop them in the chat. I'll try and check them out. If I can't get to them, Braden probably will, and we'll get you an answer. So, okay, let's get started. So you guys are probably familiar with this diagram already. This is what it looks like when you connect. This is the high performance computing diagram. So on the left-hand side here, we have the login nodes that you connect to when you log in. The login nodes have access to the shared file storage, which is basically like your hard drives, your all your files and data. In between the login nodes and the compute nodes, we have the job scheduler. In our case, this is going to be SLURM, what we're going to be talking about today. And then the job scheduler has access to all the compute nodes. You can also access the compute nodes from the login nodes, but you typically access them through the job scheduler. And then, yeah, the compute nodes also have access to the shared file storage system. So file systems and user directories, there are two file systems on Terra. There's home and there's scratch. Home is backed up nightly. And so it's limited to 10 gigabytes or 10,000 files, whichever you hit first. So there's two limits in place on them, on both the scratch and the home directories. The scratch space is larger. It's by default, you're given 1 terabyte and 250,000 files. So that's typically where people will put their data that they're going to be processing and managing. Most people will just upload it directly to, to the scratch space because it's so much larger than the home space. Home's only 10, and we don't ever increase the home file limits or quotas because home is backed up nightly, like I said, and so backing up everyone's home directories would be really hard if they're any larger than 10 gigabytes. So that's why we keep it at 10 gigs or 10,000 files. Scratch, on the other hand, we can increase, but by default, it's 1 terabyte, 250,000 files. And then you could see the usage and quota limits by using the command show quota if you're logged into Terra, which actually let me connect to the VPN real quick. 1 second. Okay, perfect. Just in case I have to log into Terra. Yeah, so that's basically the file systems. So batch computing. Here's another diagram which shows the workflow for batch computing. You start with your computer. If you're on campus, you're connected to the network. If you're off campus, you connect to the internet and then to the VPN, which allows you to connect to the campus network. Once you're in the campus network, you SSH into the login nodes. So you use the SSH utility from the command line. If you're on Windows, you're going to use an application like Mobile Extreme or PuTTY, or even like the Linux subsystem if you have like the newer Windows 10. You're going to use SSH to connect to the login nodes. So that's the command where you say SSH Dylan at Terra, that logs you into Terra. Once you're on the login node at Terra, you can create a job. So you create a job by writing a job script file and then submitting that job script file to to SLURM on Terra. And then LSF puts it in a queue, and then it finds its resting place on a compute node eventually once the resources are available, and then your output is sent wherever you submitted the job from. That's the basic workflow. So, okay, here's a sample job script for Terra. So this is what a SLURM job script looks like. You'll see all these lines here. Basically, what this job script is it's just a text file, and it's a combination of two things. First, it's a combination of SLURM directives. So all of these lines here in orange are directives, and they start with the hashtag, and then they're immediately followed by a capital S batch. So when we pass this text file to SLURM, it's going to parse the file, and it's going to see that it's going to read the lines that start with the hashtag, and it's going to think, okay, it's a hashtag, and then it's going to see that it's followed immediately by a capital S batch, and it's going to know this is a directive, and then it reads whatever argument this is right here, the double dash, and then it uses that argument to set some parameter for your job. So these are all directives. These double hashtags are just comments. The single hashtag implies a comment. So like these SBatch directives technically are comments, but they're comments that are read by SLURM. So because the entire file is actually a bash script. So like down here at the very bottom where we have this this black text, these are just bash commands that you would enter into the terminal. So this job script is actually kind of a hybrid of a bash script and a text file with a whole bunch of SLURM directives in it. So the very top, these necessary job specifications, this first block of directives, these are all the parameters that describe your job to the entire thing. All the orange directives describe your job to the job scheduler, but these the necessary ones are the ones that give the fine details of what your job looks like, its name, how long it should run for, how many cores you want to use, how much memory you want to use, and then the output, the name of the output. And then beneath that are the optional specifications. The optional specifications just specify the account you want to charge. So when you submit a job to the job scheduler on our clusters, the job will charge you SU service units, which are a form of consumable computing resources. And so this first line right here sets the account that you want to charge. So when you apply for an account, you're given by default like 5,000 SUs, and then as you submit jobs, you know, the account management system bills that account for the cost of your job. And the cost of your job depends on how long your job's going to run, how many cores you're going to use, and how much memory you're going to use. So these three parameters right here. And these next two lines just specify whether or not you want to be notified when your job starts and ends. And in this case, it's notifying you via email. So then after all these directives, at the very bottom, we have the actual bash commands that you would enter into the terminal. So here we have, in this specific example, this person is loading module load Python 3.7.0 dash Intel 2018B. So they're loading Python and then they're running Python. So when they submit this to the job scheduler looks at all these bsub directives, parses them, reads them, and finds out the resources that this job requires, sends the job to a queue and waits for these resources to become available, the time, the CPUs, and the memory, and then eventually puts it on some compute node. And then once it's on the compute node, this bottom part of the script gets run. So it would run module load Python and then /myprogram.py. So here are some important batch job parameters. We kind of covered this already. The first two right here, I actually didn't really talk about these two. These first two, --export equal none and --get user environment. Those two initialize the job environment. So they're basically setting the environment for the compute node that your job will run on. It's really easy if you just leave them like this and don't mess with them. Very rarely will you have to mess with these two lines. So most of the time, leaving them alone and not touching them is probably the best thing to do, unless you really know what you're doing. The next one is --time. --time sets the time. That's a very confusing one to understand sometimes. And it sets the time in the syntax with hours, minutes, seconds. So when you set the time for your job, that's going to be the maximum time that your job will run for. So this example right here, it's set for 1 hour and 30 minutes. So once 1 hour and 30 minutes has passed, the job ends completely. It ends, and it in the output file, you'll see an error message that says error. I believe it says like SLURM step ID job wall clock reached or something like that. So it'll just kill your job regardless of if your job was finished or not. So that's basically a hard stop. So it's always better to kind of overestimate. If you think your job's going to run, if you estimate that your job's going to run for 2 hours, maybe give it 3 hours just to be sure. Regardless, on our clusters, if you submit the job for 3 hours and it runs for only 2, you're going to be refunded that last hour. So you won't have to worry about being overcharged. You're only charged for the time that your job runs. That's specific to our cluster. Different clusters have different billing systems. So that's their policy, but on our policy, yeah, you'll be refunded the time it doesn't run. Next is --n tasks. N tasks sets the number of tasks, aka cores for the job. So this is going to be cores, total cores. So on Terra, we've got the nodes have 28 cores each, 2 sockets, 14 CPUs per socket. So for a total of 28 cores. So If you want to use an entire node, you would say n tasks equals 28, and that would use an entire node. And then down here, the next little parameter, double dash n tasks per node. This one obviously sets the CPUs per node, so cores per node. Remember I said that the nodes on Terra have 28 cores. So if you set this value to anything larger than 28, pretty sure you get an error. Pretty sure that SLURM would say, hey, we don't have any nodes with 28 cores. But regardless, it wouldn't make sense to do that anyway, because they don't exist at all. So that would never be placed onto a node to run. If SLURM didn't catch it, it would just be pending indefinitely forever and ever and ever. So you can set n tasks up here to larger than 28. So for instance, you could set this one to like 60, and then set n tasks per node to 15. That's totally fine. 60 being larger than 28, but you're dividing that total of 60 by some value less than 28, and that's valid, and that gets run successfully. And then these next two lines are right here, sbatch double dash mem, that sets the amount of memory you want your job to run. You want your job to run with, and then you can specify memory in megabytes or gigabytes. The thing to remember about Terra and SLURM is that these parameters in SLURM will set the maximum amount of memory per node. So on Ada using LSF, we specified memory per core. On Terra using SLURM, we're specifying memory per node. So we're not saying we want to use typically on Terra we're using gigabytes instead of megabytes is what I'm getting at, because requesting some like 200 or 2000 megabytes per node is like ridiculous unless you're only using like one core. So that's the big difference here. Is this is memory per node, and you'll typically see it in this format right here. Double dash mem equals some integer with the G next to it for gigabytes. So okay, mapping jobs to cores per node on Terra. So when you're on Terra and you want to divide your job up across multiple nodes, this is kind of how these are the two parameters that you're going to be looking for in your SLURM job script. Your double dash n tasks, which again sets the total amount of cores, and then your double dash tasks per node, which should be n tasks per node, which sets how many cores per node. So example A, we have 28 and 28. You divide 28 by 28, and you get 1. So here's a little diagram of that. You see the entire node is occupied. Every core on the node is occupied. Example B over here, we have 28 tasks and then 14 tasks per node. So we see that we're going to divide the 28 by 14, giving us 2. So we have 2 nodes, both half in use. And then in our last example over here, we have n tasks 28 with tasks per node being 7. So dividing 28 by 7 gives us 4. So we're using 4 nodes with 7 cores on each node. So examples B and C would probably start running before example A, because example A is using a larger chunk of, they're all using the same amount of cores, but A requires more resources consolidated on a single node compared to B and C, examples B and C. The trade-off with B and C is that as you start fragmenting your total cores across multiple nodes, these nodes have to communicate with each other more often. So depending on how many cores you're using, eventually you'd see a drop off in computation speed, because you are having to communicate so much more between nodes as opposed to just doing all the communication just between CPUs on a single core on a single node. So in these examples, using like 4 cores or 4 nodes versus 1, it might not really seem too dramatic, but as you start to scale up and start using hundreds of nodes or even tens of nodes across like thousands of cores, that could start influencing your job. So okay, let's talk about memory for a second. You also, when you write your job script, you're requesting time, CPUs, and memory. Now we said that here we're specifying memory per node. So you specify the memory request based on memory per node using either some value with an M or some value with a G. On the 64 gigabyte nodes, the usable memory is at most 56 gigabytes. I'd probably say like 54 is more of a comfortable number to hit. So what that means is that although most nodes on Terra, and this is going to be the same for any cluster that you kind of work on, when we refer to a node as being 64 gigabytes, we mean that it has 64 gigabytes of RAM installed, of like DIMMs like thrown on there. But just because it has a total memory of 64 gigabytes doesn't mean that all 64 gigabytes of that memory is available for use, because that compute node exists in a larger ecosystem, and it has to communicate with the other nodes, and it has to also run the operating system. It has to also run SLURM, for example. So of that 64 gigabytes, typically in this example, it's saying about 8. I would say about 10 is kind of a real safe bet to kind of assume that most nodes are using for running their all those background processes like I just described, the operating system, the actual job scheduler, and any of those other processes that keep the node alive. So when you're requesting memory, if you request if you want to get put on a 64 gigabyte node, you're going to have to request less than 64 gigabytes and less than 64 by about 8 to 10 gigabytes. So this just says the per process memory limit. So the per CPU memory limit should not exceed 2,000 megabytes for a 28 core job. So that's basically saying if you're using the entire node, so you're using all 28 cores, you don't want to exceed 2,000 megabytes per core to get placed on this 64 gigabyte node. Of course, there are larger memory nodes. 64 gigabytes is not the only node that we have. On Terra, there's 128 gigabyte nodes. But the trade-off here is that there's far fewer of these larger memory nodes than of the general 64 gigabyte compute nodes. So requesting or writing your job script so that you always get thrown to the 128 gig nodes you would see a reduction in time that your job takes to run, because since there's far fewer, obviously they're in higher demand, and they're more often occupied than the 64 gigabytes. That's not to say that you can't use them, because certainly there are scenarios where you need more than 64 gigabytes of memory, or 56 gigabytes of memory. So they are available. Just a heads up that that they using them might be slower. It might be slower to get on them rather. Okay, so consumable computing resources. So in the job file, you specify how many cores, how much memory, how much time you want the job to run for, and then any specific resources that you want to use. In this example, it says GPUs. So you specify those parameters in the job file, and then the account management system, along with SLURM, use those parameters to calculate how many service units you're going to be charged. Service units, like I said, are charged from your billing account, and your billing account is given to you when you apply for an account on our cluster. So if you're a student like me, I'm an undergrad, hopefully graduating in December, hopefully. But if you're an undergrad like me, you will apply for a basic account, and you'll be given 5,000 SUs. Those 5,000 SUs are yours, and they're yours alone. They can't be sub-allocated to anybody. So as you submit jobs, that'll typically be your default accounts. Like in this example down here, it says this person has this 5,000 SU allocation right here, and this is his default account. So as he submits jobs, typically this account will be charged. And you see right here, like it's being charged, it has been charged 71 SUs. But eventually these 5,000 SUs would deplete, and he'd be at 0. So once he reaches 0, this person would have to reach out to his professor, his PI, his advisor, whoever's sponsoring his research on the cluster, and tell them, who is presumably a faculty or staff member, to apply for a startup account. And once once the advisor applies for a startup account, they can be allocated up to 200,000 SUs. And the special thing about that startup account that his professor owns is that the professor can sub-allocate SUs from that account, which essentially, which is what this example right here shows, is that this user has an account right here with 10,000 SUs, which we can presume is a sub-allocated account from his PI. So in other words, the PI applies for an account and then says, this is my student, I want to give my student 10,000 SUs. So we make a separate allocation for his student, and we deposit 10,000 SUs from the PI's account in there. That's how you get more SUs. The other consumable computing resource is licenses. license restricted software such as like Ansys and stuff like that, they have licenses that are available publicly that we host on the cluster. So when you submit an Ansys job or a license protected job using SLURM, SLURM will automatically check out licenses as long as licenses are available. If licenses are not available, your job will be pending, and the reason they'll be pending is resources. And then you could go and use this license status checking tool to go check to see how many licenses are available. It's really nice. It's a really nice license status script. I like it. It's very colorful. So when you go there, it'll show you like how many licenses are available, how many are in use, and then if there's a very low number of licenses available, it'll like show up in red and stuff. So yeah, it's really cool. I think one of the other student workers wrote this a long time ago. I think it was Crystal. I think. But yeah, it's a really nice really nice tool for checking licenses. So if there's no licenses available and you submit your job will just be pending. If there's no licenses available and you try to run Ansys without submitting the job, so you just like // run your Ansys file, you'll get an error saying license is not available, and then you'll just have to wait. That's the key thing here. They are first come first serve. It can be kind of difficult to nab licenses for your job. It depends on your job as well, how many licenses you're going to need. But in the past, we have spoken with users who use a lot of licenses and told them, hey, you're kind of using 70% of our licenses all the time. Can you, these other people need to run their stuff. Can you let them run their stuff? So we like to, cooperate with our users and stuff. So all it takes is, emails and communication with us so we could work with you to find a solution. Also, if you're using the license status, script and you want help, license status -H is your friend right there. Okay, so examples of SUs charged based on job cores, time and memory. So a service unit is actually defined as the equivalent to 1 core or 2 GB of memory usage for 1 hour. Here's a little table which kind of shows how requesting more cores or more memory affects the amount of SUs you're charged. So on the very first slide of the table, we see if we ask for 1 core and 2 gigs of memory, so cores and then memory per core and then total memory. So we're saying 1 core, 2 gigs per core. So 2 times 1 is 2 gigs total for 1 hour. We're going to be charged 1 SU. 1 core, 3 gigs of memory for 1 hour charges us 2 SUs. And then 1 core, 65 gigs of memory, or 56 gigs of memory, sorry, for 1 hour charges us 28 SUs. So as you start requesting more memory and more cores, you're going to see the SU charge increase a lot. So you can go through SUs pretty quickly. When you inevitably run out, it's best to email your professor and tell them, hey, can you apply for a startup account so I can get more SUs. People use the SUs. 5,000 is really not a whole lot. So most people will use their basic account pretty quickly, especially when they're first getting started, because they don't really have a great idea of the resources they need. So they kind of brute force their way through it. But the longer you use these systems, the easier it gets, and the more refined you can make your job scripts, so you know exactly what you're doing, and you're using the exact amount of resources so you don't waste as much, is the key. So batch queues. Job submissions are auto-assigned to batch queues based on the resources requested. The resources requested being the number of cores and nodes and the wall time. Some jobs can be submitted directly to a queue. On Terra, if the GPU nodes are needed, for example, you'd use the GPU partition, the directive for that is -- partition. SLURM calls them partitions. In our heads, we kind of think of them as queues because that's what they are. They're queues or lines for your job that they wait in before they start. So specifically in SLURM, selecting different partitions, you'd use the -- partition. In this case, you say -- partition equals GPU. Jobs that have special resource requirements can be scheduled in the special queue, but the special queue is a protected queue, so you have to have access to, you have to have a little flag on your account to be able to access it. That starts with an email to us. So if you have a special a special resource requirement that would otherwise be hard to get normally, just kind of organically through the natural ecosystem of the cluster, send us an email, and we'll work with you and schedule a time for you to jump into that special queue. So the jobs jobs are auto assigned their queues based on how many cores and how much time your job's going to run for. So because they're auto assigned, you don't have to use the partition, which is why it's not a necessary specification that we saw in that example script. So if you use the partition and you try to kind of game the system, and that your job would, that the resources that your job is requesting would put it on a like, let's say, a longer queue, but you want it to run on the short queue because the short queue is a lot shorter than maybe the line in the longer queue, and so you were to say double dash partition equals short, you'd get an error, and the error would say you don't have permission to do this because the assignment of queue from SLURM is going to supersede the assignment from your job script if you don't have if you're not like if you could see my air quotes right now, a SLURM administrator. A SLURM administrator just being someone who's running sudo SLURM commands, which is not going to be any user, it's going to be the admins and stuff, which we never do unless we're doing maintenance and trying to pick apart the machine so we can make things run more smoothly. Okay, next. So here are the queues, aka the partitions. You see we have short, medium, long, GPU, VNC, extra long, staff, priority, special, and then KNL for the Knights Landing nodes. So you can see these queues using the synfo command on Terra. Synfo being slurm info shows us all the info for the queues. In our case, this is what they look like. The way you'd read this is you'd see right here, it says, so obviously the first column gives us the name of the queue, the name of the partition. And then over here, we see how many nodes are available and how many CPUs are available in this core, in this partition. So here we see nodes, and then these slashes differentiate available, idle, offline, and then total. So, oh, I'm sorry, active. Active is active, idle, offline, and total. Yeah. So active is how many are currently in use. Idle is the one that you would look at, being how many are available for use. And then offline is the ones that are taken offline because maybe they have there's some issue with them that we're working on. And then total being just the sum total. And then on the other hand, on the next column over, we have CPUs, which is just the nodes, this number multiplied by 28 because there's 28 cores per node. Yeah, and so that's basically how you're doing Synfo. Synfo is useful when you're submitting a job, and then your job is pending. So what queue your job has been placed in. You could run Synfo and then find the current status of that queue, and you could kind of see, oh, okay, well, it's a very busy queue right now, so I'm going to be waiting for a little while. But the biggest thing that differentiates these queues from one another is the time that the jobs can run for. So if your job is in the short queue, it shouldn't be pending for more than like 2 hours, because most jobs there will only run for about 2 hours. So that's the idea there. Okay, so queue limits on Terra. So I'm not going to go through this entire table, but the idea here is that the queues have maximums. They have maximum limits for how much time the jobs in those queues can run for. That's why we divide them up so they can run real quick. So like I said before, if you have a job that's been placed in the short queue, the maximum wall time for jobs there is 2 hours. So if you're waiting 4 hours for your job to run, the queue is either super busy, or which is probably not the case, or there's some kind of issue with your job script. So if your job is pending for a really long time, you'd probably send us an email, and we could take a look at it. There's also limits on how many cores you could use per use, how many cores each individual user can use across all queues. That's so one person can't hog all the resources. The whole reason we have these limits in place is to what's the word? Promote the sharing of the resources. We don't want a single person to be able to use all the resources at a single time, because this is a shared computing resource. So SLURM helps us facilitate the sharing. So actually submitting your jobs. So you write your job script, example 01.job being the job script that we have written. And then to actually submit it, we call SBatch. So we say SBatch, which calls example job. We call SBatch, which calls SLURM, and then we pass SLURM example 01.job. And then this is what it looks like. It says submitted batch job, and then it gives us the job ID. And it says your job is charged as below. It says from this project account, which has this balance, we're going to take, you're requesting 3 SUs. And then it submits it. And then right below this, which we didn't include in this little photo, but it would say job example 1.job submitted to, and then it's going to give you the name of some partition. So it's like the medium queue or something like that. So that's how you submit your job. Once you submit your job, you're going to see, you'll see right here, you can check your queue, or sorry, you can check the status of your job using SQ. So SQ shows you all the jobs for the user. SQ minus U will show you all the jobs for the user. SQ by itself will show you all the jobs running on SLURM to begin with. So SQ by itself is not very useful. SQ minus U, given the net ID, is what we're going to be looking at. So in this case, we search for net ID, and we see, in this case, the person's net ID is some user, and we can see all the information about their job. The first column gives us their job ID. The next is the name of the job, the user who submitted it, the partition it's running in, how many nodes it's using, how many cores it's using, its current state, is it pending, is it running? If it's running, how long has it been running? How much time does it have left? What time it started at? The important thing for SQ is when you submit your job, you can run SQ and you'll probably see that it's pending. So it'll look like this first entry right here. And then when it's pending, you can go over here to resources and you can go over here to reason, and the reason that it's pending will change. In this case, it says resources. So we know that SLURM received the job, it's a valid job, and it's waiting for the resources to be collected. So the asterisk next to that is if you make an incorrect request for resources that SLURM doesn't catch for some reason, your job could be pending forever. When you submit your job, you should double check that it's pending. First off, that your job actually got submitted, and then give it some time. You got to be patient, as with all things in life. And then once enough time has passed, if it's still pending, then yeah, maybe double check with us, send us an email, and say, hey, I submitted my job, still pending for resources. What's going on? And like I said, one of us will take a look at it, and we'll see what's going on. Okay, so let's take a look at another job file. This case, in this example, we're looking at a multi-core single node job. So we have a new little parameter here, a new little directive. This one's going to be double-dash nodes, which specifies how many nodes you want to use. So here we're saying 1 node, 14 cores. So we're not asking for total cores now. We're just saying 1 node and then 14 cores, 28 gigs per core. And so it looks like this up here. We see we have 1 node total. We're using half of it, and then we're using roughly half of the memory on it too. So we're being charged 91 SUs because we're also running for 6.5 hours. And then all this other stuff down here stays the exact same. The only difference is you see these two right here. This output, this extra line right here, double-dash error, will send all the valid output will go to standard out. And if there's any errors that are thrown by this job or any of these commands, those errors will be sent to standard error. So this just creates 2 separate files. Some people prefer that. I might prefer to have it as one big file. But you can split up the standard output and the standard error to do 2 different files if you really want. And then down here we see the exact same thing. These are just bash commands. So module load intel, and then /run my multi-core program. So the key takeaways from here is that you can specify how many nodes you want specifically, and then explicitly set how many cores per node. which might be a little easier than to do the whole division thing. In my case, I prefer using, I prefer the other way. I just, the implicit setting of the nodes versus the explicit where you say, okay, I want one node. I prefer the implicit way where you set how many cores and then you divide how many cores by how many cores per node, and then you get the total number of nodes. But that's just how I prefer. To each their own. So here we're going back to doing that implicit node request here, and we're saying this is a multi-core, multi-node, so many cores across many nodes, 8 tasks, so 8 CPUs total, and then divide that 8 by 2 gives us 4, so 4 nodes, and we're putting 2 cores per node, and then 2.5 gigs of memory per node. So up here in our little diagram, we see 2, 4, 6, 8 cores divided across 1, 2, 3, 4 nodes, gives us 2 cores per node. Again, all this other stuff doesn't change. In this case right here, we're just sending the output and the error to the same file, standard out. These bottom ones haven't changed at all. And then over here, we see the same thing we've done. We've module loaded Intel and then ran our little program using MPI run this time around. We are being charged 288 SUs this time around. That's because we are requesting much more time. So the syntax for this time right here looks a little different because now we're saying 1 day and 12 hours. So the syntax before that we were familiar with was hours, hours, minutes, minutes, seconds, seconds. That's good as long as you're requesting less than a day or exactly 1 day, which actually I guess you could request, like 72 hours. I guess that would work. But okay, that's too much division. So at that point, I prefer this method right here where you implicitly say how many days you want to run. So this syntax is a number followed by a dash. So the number specifies how many days. So 1 day dash, and then our old familiar hours, hours, seconds, seconds, minutes, 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 seconds, seconds. So 1 day, 12 hours, and no minutes. So I prefer this time, this syntax compared to the implicit of the division. That's because I can divide by this a lot easier than I can divide by 24 in my head. I don't know why, but yeah. So in this case, that's what they're doing here. They're setting the time. Okay, serial GPU jobs. So we want to request a special resource. In this case, we want to request a GPU. Serial implies that we're running on one node. We're not running across many nodes. We haven't parallelized our job, so we're not using parallel computing here. So job name, job example 4, time set to 1 hour, how many cores and tasks equals 1, how much memory, 2 gigs per node. Send all the output to standard out, both the good output and the bad output, standard out, standard error. And then right here, we're saying SBatch, G resource equals GPU, :1. So what this is saying is I want to reserve this resource. I want this resource. What resource do you want? I want a GPU. How many GPUs do you want? 1. So on the nodes, there's actually 2 GPUs per node. That's like the most we can fit in there. Like literally, the physical size is the limitation. Well, actually, I can't take that back. I guess there's only 2 slots. Yeah. Well, anyway, so there's 2 GPUs per node. And then this case right here, we're reserving one of those GPUs. And then this next line says, we're familiar with it. This says, set the partition to GPU. So it's going to put us in the GPU queue. So you might be wondering why over here in our little diagram, we see 1 core on the entire node and 1 GPU for 1 hour, but we're still being charged 28 SUs. That's because if you request any special resource in SLURM, in this case, you're only requesting 1 GPU and 1 core and 2 gigs, but you're being charged as if you requested the entire node. We found this, we discovered this a while back, like 2 spring breaks ago. And for some reason, that's just how SLURM does it. So SLURM calculates these resources as if you're requesting the entire node. So if you request even 1 GPU, it does not make sense to request only 1 CPU. If you're using any amount of GPUs, you might as well use the entire node because you're going to be charged for the entire node. So this would run perfectly fine, but you're just limiting yourself because SLURM is going to give you the entire node to run on. So it's going to give you the entire node to run on, and it's going to charge you for the entire node to run on. So you might as well give yourself access to the entire node since SLURM is going to do it for you anyway. So if you're requesting resources, you got to include these two lines: gres equals the resource you want to use, in our case GPU, and then you'd set colon to 2. That's going to give you access to GPUs 0 and 1. It starts counting at 0. So 0 is the first GPU, 1 is the second GPU. And then you set the partition to GPU. And then down here at the bottom, you do all your little setup. So in this case, we're loading Intel, we're loading CUDA, and then we're running your GPU program. So yeah, if you're requesting GPUs, just request all the CPUs on the node because you're going to be charged for it anyway. Other types of jobs. So the other types of jobs are MPI and OpenMP jobs. MPI being the message passing interface, and AKA for parallel jobs, parallelization. Those are for when you're running across many nodes, which was like that multi-core example we saw a while back. The other are visualization. Visualization jobs are jobs that can be run on both Ada and Terra. They're basically, so if you want to run like the MATLAB GUI or something like that, that would be a visualization job. You could do those from the portal. The portal is a web-based access. If you're doing visualization, I would highly recommend using the portal because it's a very clean way to access visualization jobs. If you're using if you're making or wanting to submit a large number of concurrent single core jobs, you could use Tamu Launcher. Tamu Launcher is a wrapper script written by one of the staff members. You can find a whole lot of information about it on our wiki, hprc.tamu.edu/wiki, which I plug like every primer I do because that's where I literally learned everything about HPRC. That and from my the two coworkers I was working with at the time when I was the new person. But the wiki was my home for many months. So go to the wiki and either search Tamu Launcher or go straight to that link, software:/Tamu Launcher. It's useful for running many single core commands concurrently across multiple nodes within a job. It can be used with serial or multi-threaded programs. It distributes a set of commands from an input file to run across the cores, and it can only be used in batch jobs. So if a job gets killed, you can resubmit it. You can resubmit the same job, the same input file to the job, and it'll finish running those commands. It's very useful for, like I said, for many small jobs. So take a look at that wiki page for more information. I haven't checked the chat actually, so let me go. Okay, yeah, Brayden's got all that. Perfect. Okay, so job submission and tracking. So here are some important lines to use, some commands. SBatch, we already said, lowercase SBatch submits the job to the batch system. SQ lists the jobs. Remember, SQ with no arguments lists every single job. Not really useful. It'll just kind of spam your screen. But I guess it's kind of cool if you want to just see what's going on Terra. So you want to use SQ with the -u flag and then the username. SCancel is what you use to kill a job. So let's say you submit a job, but you know you're going to get an error, or maybe you want to resubmit it for some reason. The command you'd use would be SCancel, and then you pass SCancel the job ID. You get the job ID from SQ. That just kills the job outright. If you try to SCancel someone else's job, you won't be able to, because obviously you're not like a SLURM administrator. So don't worry about being able to cancel other people's jobs. If you can, that's really weird, and you've broken something somehow. So send us an email. Although like I'm 99.999% positive that would never happen. SAccount shows information for a job. So you can only run SAccount. I'm talking about right here, SACT. When the job is running or when it has just finished. And then also you pass to that the job ID. These other ones down here, LNU and PEstat, these are for showing resource usage for a job. The key difference being that PEstat can only be used on a running job, whereas LNU can be used on a job while it's running or after it's finished. LNU, which stands for list node utilization, you pass out the job ID. In PEstat, you give it your username to check. And then Ceph also works too, but to be honest, I'm not very familiar with Ceph. So LNU and PE stat. So checking your service unit balance. We talked about SUs and stuff. So as you submit SUs, you're going to be as you submit jobs, you're going to be using SUs. You can check your balance by saying my project. Specifically, it's going to be my project-L. This is the output you'll get. We're kind of familiar with this. The first line shows the allocation number. The next column shows the year for the account, the fiscal year. The third one is whether or not it's default, how many SUs you were given, how many have been used, the current balance, and then the PI. To change these defaults accounts, it's going to be my project minus D and the account number. So to change the default account of this first one, you'd say my project minus D. You'd copy this number right here, hit enter, and it's going to change this Y to an N and this N to a Y. So this first one would be the default. The default account is the account that gets charged when you omit the minus P optional specification. So, oh, sorry, not minus P. I'm thinking about LSF. If you omit this for right here, this double dash account, if you take this out because it's an optional job specification, you don't need it. If you take it out, Terra will SLURM will just charge your default account. So without that line, this middle account right here would be charged. If you try to set that number to somebody else's allocation, so for instance, you ask your PI, hey, what's your project account's allocation? Because mine ran out. If he gives you the allocation number, you can put it in there, but it's going to give you an error. You're going to get an error at the time of job submission, and AMS is going to say you don't have permission to charge this account. So you could try it, but it won't work. You have to ask your PI to sub-allocate USUs, which can be done either through the website, hprc.edu/AMS, where you actually manage your accounts, or by sending us an email and having your PI send us an email, and then we do the sub-allocation for them. So job submission issue, insufficient SUs. When you run out of SUs eventually, like we all do, this is the error you'll get, SPatch error, your account balance is not sufficient to submit your job. This person's got 382 SUs and he's requesting 18,000. Quite the difference there. So when this inevitably happens, send an email to your PI and say, hey, I'm all out of SUs. Do you have a startup account that you can sub-allocate SUs to me from? If they say yes, then have them send us an email, or because we all know how busy professors can be, you can send us an email, CC your professor, and have your professor just reply to your email and say, yes, I approve of this transfer. That's typically enough for us. We just need the paper trail to know like that your advisor, your PI approves of the transfer of SUs. So you can initiate the request, but we need the advisor to approve of it via email to us. Yeah, okay, and then here is LNU, list node utilization. This is what it looks like. So you give LNU the job ID, and you see over here, it gives you the host names that the job is running on. Host names being the names of the compute nodes where your job is running. The CPU load being how much of the CPUs are being used, and then free memory and stuff. CPU load is not the same as percent utilization. It can be excuse me. It can be kind of hard to debug this, but the general idea is that you're looking for, this kind of gives you the efficiency of your job. So, you know, you can request all the cores on the node and then run your job, but you know, maybe your code itself is actually not utilizing all of the CPUs efficiently or as much as it should be, in other words. So this is how you would check that. Same deal with PE stat. But yeah, you give LNU the job ID, you get the job ID from SQ. Or you can see LNU minus H for more options. And then here is PE stat. PE stat basically shows the same things, but this is going to be for running jobs. So it shows you the CPU load, how much memory is available. So you can see right here, it says free memory is about 55 on these 65 gigabyte nodes. This over here, these names TNXT, those are actually the host names of the compute nodes. So on Terra, the compute nodes are named TNXT dash and then some numbers, zeros, in this case 0703, and then they just count all the way up to some number, which I totally forget. But TNXT is Terra's compute nodes. On Ada, they're actually called NXT. So NXT dash like 0304. That's the name of Ada compute node. So, we saw if you were in the other classes, like the introduction to the Terra primers and stuff, when we log into Terra, we see the login nodes are named like tlogin 0501 or something like that. Those are the actual host names. And then we just, we forward from like the terra.tamu.edu. That domain name just pushes you to these hosts, or not to these hosts specifically, but to the Terra logins. So back to PStat, low CPU utilization will be shown in red. Good is going to be highlighted in purple, and then I guess ideal would be shown in white. So again, a very colorful script. Typically, the more colors you add to your script, the better your script's going to be. That's just how those things work. Job environment variables. So on Terra, whenever you submit jobs, the job scheduler is going to have its own some of its own environment variables that it's going to use, which you can also access too. So as you get better and better working with SLURM, you could use these environment variables. A few key ones are going to be the SLURM job ID. So $SLURM_job ID obviously returns the job ID for the job. The submit directory is going to be found in SLURM submit dir. That's going to be where the job was submitted from, which is also where your output's going to go by default. So wherever you submit it from, remember that's where it'll be. Scratch is going to be, the Scratch file system. So /scratch/user/netid. And then the temp directory is going to be the temporary directory for your job, which is going to be local to each assigned compute node. And it's going to be about 850 gigs. So if for some reason your job needs to use a temp directory, that's a great one to use. Just remember that this directory is going to be local to each compute node. So you have to do some magic to get it to be communicated across nodes. But yeah, it exists about 850 gigs. Lastly, we're talking about Tamu Batch. So Tamu Batch is an automatic batch job script that submits jobs to the user without the need of writing a full script. You can access it with logging in to Ada or Terra. So on Terra specifically, and you say Tamu Batch. What you give to Tamu Batch is you give it a file with a whole bunch of parameters for your job. And then the cool thing about Tamu Batch is that it'll build your job for you. So it takes the parameters that you give it, and then it actually creates this file all the way back to the front. It creates this file for you. So it'll give out all these SBatch directives, so you don't have to type them out yourself. You could do that. You can use Tamu Batch to create this file, or what most people do is they go to the wiki, hprc.tamu.edu/wiki, go to the Terra quick start guide, go down to the section about job scripts, and they take all this text, copy it, paste it, and then just change these parameters. That's the easiest way to do it. That's how I learned to do it. Totally viable. Eventually you'll just start remembering all the necessary stuff that you need to write. Or if you don't want to do that, you want to be a little more original, you could use Tamu Batch to help us out. Because this little script is kind of still in beta. This one was actually written by Kyle, who's another student worker here. So any feedback we get on that script is really, really helpful to us, because then we can refine the script and make it more helpful to other people. So again, Tamu Batch will give it some parameters. It'll build the job script for you if you don't want to copy paste from the wiki. Try it out and let us know how it works. Lastly, the portal. I talked about it before. This is a web-based. This is all web-based. So when you log into the portal, you can access it through any web browser anywhere. So it doesn't matter what operating system platform you're on, Mac, OS, Linux, Raspberry Pi, I guess. You could access the clusters, and you could submit jobs. You could check your files. You could compose job scripts. You could launch interactive GUIs, and you can even access the command line by going to clusters and then getting shell access. So Ada and Terra both have their own portals. So portal.hprc.tamu.edu takes you to this landing page right here, and you select Ada or Terra, and then you have the choice of doing anything, managing your files, accessing the shell, or just starting jobs straight from there. So that's all I've got for today. Finished 55. So if you guys have any questions, I will stick around and answer them. But yeah, so thank you guys for coming. I think next week, that's all for this week. Next week is, what is next week? I think next week on Tuesday is data management on the clusters. So I appreciate you guys coming. I think there was a question. Oh, I'm sorry. I don't know if I closed that for everybody. Is the portal instead of MOBA Xterm? The portal can be used instead of MOBA Xterm. Yeah. If you, it's all preference. If you have MOBA Xterm and you want to use MOBA Xterm, that's fine. If you like are using a computer where you can't install MOBA Xterm and it has a web browser, then you could go to the portal and you could do everything from MOBA Xterm that you could do from MOBA Xterm through the portal as well. It's just another way of accessing the cluster and running like biz jobs and stuff. The slides, yeah, the slides are posted. See, did Braden post it? Right there. Look at Braden. Damn, he's good. The slides are there. Yeah. Primers pop up. If you go there, you're gonna see all the slides for all these pop-up courses we've had. So what are the files in Scratch and Home that can be deleted since there are limits on the number of files? So those, whatever's in those directories are yours to manage. So if there's files in your home, you could delete anything that's there. If it's in your home or your Scratch, typically you own it unless one of the staff members puts it there. In which case, if we put it there, then you should be able to delete it. Since there are limits on the number of files, yeah, and you want to delete your files. So let me show you this real quick. So I'm gonna log into SSH. Log into Terra real quick. No problem, Christopher. It's my pleasure. Let me log in real quick. Okay. Yeah. So some of the temporary files, like if they don't get deleted automatically, then yeah, you'll have to go in there and delete them. So like when I'm in my, right now I'm in my home, right? Because I just logged into the cluster. Oh, okay. Show quota. So when I show quota, it says I'm using 3,000 file, 3.5 thousand files out of 10. But when I ls or ll, like it only shows like all these files. So what you can do is do ll minus a, and it's going to show you all your hidden files. So there's a lot more files here, so you'll have to go through here and figure out which of these files you don't need, and then to remove the files you don't want, you just do rm. Rm deletes the file, and rm minus r deletes the entire directory. So like if I want to delete this scripts directory, I'd say rm minus r scripts, and it's going to delete scripts and everything in there. Thank you guys for coming, by the way. No problem, no problem. Any other questions? Awesome. Okay, well, if you think of anything else, just send us an email. Thanks for coming.